Alright, welcome to our fourth video. This time we're going from the Bohr model to the quantum mechanical model. So, the Bohr model is great, but kind of had some flaws. To start with, let's kind of go with what it mainly centered on. It's got two main ideas. Again, electrons exist only in certain discrete energy levels. Now, these are described by what we call quantum numbers. We're not going to focus on those. Put simply, the kind of chemistry community determined that using quantum numbers really doesn't help you learn much about anything. Kind of just makes chemistry more complicated. Doesn't really teach you quantum theory. So we're not going to worry about that. What you got to care though is that they are discrete levels. So, and those levels do refer back to the quantums of energy that Planck and Einstein were talking about. And two, energy is involved in the transition of an electron from one level to another. Basically, whenever electrons go, they need to absorb energy whenever they go to an outer shell, and they will release energy and fall back down as they're coming down. In fact, actually, if, for example, we were able to give electrons enough where it actually goes past the max energy levels of that atom, well, that's how we start forming ions. They actually are lost and can be transferred to something else. Well, not lost, they're transferred, if you will. So anyways, these are great, but upon closer examination, it becomes evident that light can sometimes act like a wave, as we initially talked about, and as a particle, as Einstein pointed out. There's a few experiments I can have you look up. It's called the double slit experiment. There's actually a recent picture they got of light being a wave and a particle. It's really cool. But basically, light can be both. Not just waves, not just particle. It really depends on the circumstances. And no, I don't know what circumstances to make it a wave or a particle. I'm not sure if anyone actually knows quite yet. But we're still working on that. So in 1913, Louis de Broglie posed the question that if light had a dual nature, couldn't matter also act like a wave? Which, I mean, think about this. He's basically saying, can matter, like you and me, actually be a wave? Like, do we have a wavelength? And at first everyone's like, no, that's stupid. And then they're all thinking, well, wait a second. Why not? So he thought so. And he proposed that electrons, at least, moving about the nucleus of an atom, behave like waves. They at least have wave-like properties. And thus, they actually even have wavelengths, which is just weird to think about. But he ended up actually kind of being right. So he proposed that the wavelength of an electron, or really any other particle, depends on its mass and its velocity, which, by the way, in physics we call the momentum, but we don't care about that right now. But h is, again, Planck's constant. So he says that the wavelength of really any object is only dealt with Planck's constant, its mass, and how fast it's moving. So let's look into that. He then, by the way, coined the new term matter waves, basically to describe wave-like particles of matter. So particles of matter that are acting like waves. So kind of weird and actually really phenomenal, because typically people thought things could be particles or waves, and he's saying, yeah, well, there's these things that do both. And they're like, what? So anyways, what is the wavelength of an electron moving with the speed of that, and the mass is that? Yeah, I got tired of reading. So we got that our wavelength is equal to Planck's over our mass times our velocity. Well, we have our velocity, we have our mass, and you guys know Planck's. Try and figure this out. Spend a few minutes. Okay, welcome back. Let's plug in numbers and figure out these wavelengths. So, plugging those values in, you get about 1.2 times 10 to negative 10, which is about 0.12 nanometers. If you actually go back on, there's a chart in your book if you'd like. These are basically X-ray. Kind of, that's the wavelength of these. But again, that's an electron. So this electron is likely coming from, I'm sorry. similar to the wavelength of an X-ray. So, kind of cool. So, while the discovery of matter waves was great, it kind of posed a really annoying question. Because we're trying to locate electrons. Now we've got that they're particles and waves, but where are they? And the issue is that, where do I say that wave is? Do I say it's here, 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 all the above? It's really kind of annoying to define the location of a wave, especially since actually they continue on forever. So, in 1920s, Mr. Heisenberg proposed his uncertainty principle, which basically states that since matter can both be a particle and a wave, it is impossible for us to simultaneously know both the exact momentum and the location in space. So we can know one, we just won't really be able to know the other. We can figure out how fast it's going, but not really know where it is. Or we can figure out where it is, but not really know where it's going. So he kind of basically just said, well, you'll see. In 1927, Erwin Schrödinger then proposed his quantum mechanical model of the atom as a solution. So he took Heisenberg's, he took Bohr's, and basically said, let me kind of make these make a bit of sense. Well, he tried. And succeeded, but it's still crazy. The quantum mechanical basically completely ignores trying to actually locate an electron. It basically just kind of gives up, because Heisenberg says you're not going to be able to do this. It really just doesn't care. It's not going to really deal with that. It does take the idea of kind of energy levels of Bohr, but doesn't quite approach it the same way. He develops areas in which electrons are likely to be found. So here's our nucleus, and basically this is kind of the area that an electron could be found in. Now I'm not saying each of those are electrons. It's typically a lot deeper. But it's basically like all these are almost positions where an electron could be found. It's one of the ways found someone describe it. It's basically if every time the electron moved, it left a little red dot to track where it had been. And you let it move around and stuff, you would end up having basically this cloud of electron possible locations. And that's what Schrödinger ends up actually saying is how you can locate an electron. So yeah. So instead of trying to find the electrons precisely, Schrödinger treated electrons like standing waves. Basically, imagine two pieces of wood, I guess, and a string that's vibrating between them. More so, string and then you're vibrating. I'm not a musician. Imagine a guitar string. Like, the string's not going anywhere. It's not changing its location. Still a little bit unsure of where to say the location is, but we know it's not moving. So he's basically saying they are waves, but they don't really travel in space, at least instant by instant. So he then calculated a probability density function, meaning he calculated a cloud that factors in the density of the likelihood of finding an electron with that, meaning the more dots, the more likely it is to find an electron there. Okay? And again, focusing highly on probability. This function then allows us to determine actual areas of space where an electron is very likely to be found. Now, there's places where they're not likely to be found. We end up having kind of the concept of subshells, where basically this is more likely than somewhere else, but not really as likely as somewhere else. So we kind of have this kind of intermediate state. But it still helps you determine areas where electrons probably are going to at some point be found. And they do end up following a similar path/structure of the Bohr model, but again focuses on probability instead of an actual set path. By the way, a region of space where an electron is likely to be found is called an orbital. That brings us back to electron configs, which we're getting to next. So that leads us, again, to our current model of the atom, which is a nucleus surrounded by an electron cloud. Commonly called the cloud model, by the way, but quantum mechanical gets you, it's the more official name, if you will. And that basically, again, comes down to a nucleus surrounded by a bunch of dots in a somewhat cloud shape. All right, thanks for watching.